So that's great. Energy is a state function. So the types of energy we need to worry about usually in chemistry, potential energy, for example, gravitational potential energy, that happens if you're dealing with a chemical reaction in a beaker. That doesn't really matter that much because there's not much of gravitational change that's happening. If you're dealing with a plant, that actually can matter. If you have a pipe coming in up here and ending up down there, then it'll actually gain gravitational energy as it goes down. So that can matter. But we probably won't deal with it that much in this class. All that matters there is how high is it. Chemical potential energy. This is important. We need to find the energy of that particular configuration of atoms using Schrödinger's equation. However we know it, the configuration of the atoms affects the chemical potential energy, and a different configuration of atoms will have a very different potential energy. And indeed, it's usually much larger than the potential energy due to the location of the atoms due to gravitation. Kinetic energy. This is another very important type of energy, and that's we'd see in the motion of large objects. If you had some fluid flow coming from a higher elevation down, that matters. Weather, as we've seen, we've had some pretty crazy weather. There's energy involved in masses of air coming down the mountain, picking up kinetic energy from that descent. So we measure their velocity if we're interested in the kinetic energy of large objects. But the motion of small objects, the kinetic energy matters as well, all the wiggling and jiggling of the atoms. And so what we need to worry about, what we use to measure that there is the temperature. So we can measure kinetic energy if it's big just by measuring the velocity and knowing its mass. If it's small, we only have to measure the temperature. And that's essentially telling us what the kinetic energy is. I mean, it's just in some ways a way to measure the energy just by, exposing the system to a thermometer that was calibrated to let us know, so it rises to a certain extent or it gives a certain number based on the kinetic energy it senses from the molecules around us. So that's how we would measure the energy. Okay, so that's the type of changes in energy of a system we need to worry about. But of course, if we have a system and the surroundings, we also have energy transfer between the system and the surroundings. So we know about the changes in the energy of a system that we'll have to worry about. How do we worry about, what are the kinds of energy transfer we'll have to make sure we're aware of? So that's key, is we can keep track of the total energy. Since the total energy is conserved, we can keep track of the total energy by measuring the energy that is transferred between the systems and surroundings. So we just know about how that energy is transferred. We can calculate changes in energy in the system. So mechanical work is one common way. Chemical reaction moves the surroundings, like expanding a balloon or driving a piston. And then some really cool stuff. I'll link to it on the page about the history of James Joule, for whom the Joule is named, who did some very fun work with paddles turning water and heat giving off there and making very careful measurements and showing that the energy of the mechanical work was turned into thermal energy. It's interesting, he actually started as a brewer and actually started doing science just on trying to understand the family brewery and how to improve that. So I'll send some links to that history. Okay, so mechanical work. So chemical reaction can move the surroundings, like expanding a balloon or driving a piston. That's where we get how automobiles work, is that there's a chemical reaction with an explosive amount of gas. It moves a piston, and the chemical energy is turned the molecules that are reacting push against the piston and do mechanical work on their surroundings. Heat transfer is an important way that energy is transferred. So the thermal energy from vibrating molecules is transferred from the chemicals to the container to the outside. So you have some jiggling of the system and it's in contact with its surroundings, and that results in more jiggling of molecules in the surroundings, or the system doesn't have, the molecules are not jiggling very much, it's cold, and therefore the faster, the more jiggling from the surroundings is transferred into the system. So an important thing about work and or heat is there are not state functions. Not all functions are state functions, and so work is not a state function. The work that to go from initial state to a final state, if you do it a different way, you will very likely get a different amount of work. And the same thing is heat. If you take it from one initial system from one initial state to one final state, even if the surroundings are in the same initial and final state as well, the amount of heat transferred over the course of that process will be different. So those are not state functions. You have to remember that. Yeah. So yeah, the amount of work depends on the process, not just the start of the end point. So being a state function is something kind of special. Not all quantities are state functions. Yeah, electrical work is also an important part of work that occurs in chemical systems. We're going to talk about that later near the end of the semester. Units of energy. So you'll see a number of different units of energy. Joules is the most common. That's the SI unit, kilograms meters squared per second squared. Kilojoules is sort of more the size of the energies that happen in chemical reactions. So that comes up a lot. Calories, small c calories. It's a 4.184 joules. I put a star there because there's a couple definitions of calories, which is really annoying, that are all around 4.1 something, but not the same. So it's the amount of energy to heat 1 gram of water by 1 degree C. It turns out that if you have hot water or cold water, it's a slightly different amount of heat. And so you get, you know, steam table calories being slightly different than thermodynamic calories. It's sort of a mess. So generally, what the conversion factor is, it's 4.184 unless you look it up and you're actually dealing with a slight, it's a steam table calorie or a 4 degree C calorie. But those can be looked up, those conversions, which is why it's usually easy to work in joules, and we'll mostly work in joules occasionally. We'll do some problems with calories because those do come up. The calories when you eat food, it's the same calorie. I say a calorie is a measure of energy, except usually it's a big C calorie, which is 1,000 small c calories. Isn't it nice with the SI units, we actually have things where you have to put a number, you put a letter in front of it to indicate if it's bigger or smaller, rather than just making a, you know, can you tell the difference between a handwritten big C and a small c? It's kind of hard. So be aware that usually if it's the small c calorie in a problem, it's 4.184 joules. If it's a big C calorie that you'd see on a food wrapper, that is 1,000 of the small c calories. So it's about 4,180 joules. A kilowatt hour is very common when you're dealing with electric energy. So that's actually a much larger unit, 3.6 times 10 to the 6 joules. A liter atmosphere is not used all that much, but it shows up in intermediate in calculations all the time. And that's about 100 joules. There's a nice table in the book I'm just reproducing here just to give a sense of how big these things are. You can see that a joule is really not that much energy. The amount of energy used by a human body in running 1 mile, about, you know, obviously depends on the weight and speed and everything, but, you know, like 4 times 10 to the 5th joules. So it's a lot of joules. Whereas it's about 100 calories and it's about 0.12 kilowatt hours. So these units of energy can be very different in magnitude. Remember, a joule is pretty small. A kilojoule starts to be a little more reasonable. Actually, in most packaging in Europe, you'll see that they actually list the energy not in calories, but in kilojoules, which is nice. Makes it more clear that it is indeed the same quantity that we define in terms of energy. Yeah, so you can see, yeah, it's a useful table to look to get a sense of how big things are. Joule is not very big, which is why kilojoule is used quite a lot.